Okay, wonderful people. Let me give you your opening statement, if you will, your summation. I'm going to show and talk about elongation problem with the structure and how it got there. It'll be very obvious when you see it all together now that we've got the OSHA report, and I now see probably everything but the canopy, right? As far as cracks, they could show me more in the bottom. It wouldn't change. Even the canopy, it wouldn't change. So let's go ahead. It wouldn't change my data. I would need something else to change my data. Something like we left off post-tensioning in these members 100%. We never did it. Something like that would change. That's my 99.9% confidence. Now, the format will be such that I'll jump from the floor to that one structure to the video. And I think I'll jump right into the video and give you a nice opening teaser to give you supporting evidence, if you will, if this could be considered evidence, based on the plans that we have 2017. We see main deck span D1 is what they did. That is what we know they tensioned before they did C2, before they did number 2 and number 11. D1 was done in canopy transverse, a longitudinal cable C2. D1, as I talked about previously, is 527 kips. If we look at the live end, it's 471 kips. At the far end, it's 489. And let me go ahead and jump right into that. Talk about that. Everyone speaks of how come it didn't fail at the other end, the south end. Well, the south end has a different configuration of the nodal area of 1 and 2 compared to 11 and 12. 12 is sitting off the deck by about 10 inches. Number 1 is on the deck fully. It has a larger diaphragm. And it has the higher anchor force set. It's a 489 kips, so it's got a higher loading there also. 471 is where this is the failured end. The failured end. All right, so I do mess up on some words now and then. You guys can have fun with that. I'd rather you just correct it for me down below. Of course, I'll take offense to it, but that's the way it is. All right, 471, 489. We look at C2. C2 at the failured end, so we get the C2 on your canopy. Here's C2. We follow C2 over. 426 is on the live end. That's the end we see. And then on the far end is 459. So you have a larger force, as I tried to explain to you guys about how this is not as uniform as you would think it is with the transfer loads. Think of that as a free body diagram where you can see that, wow, it's stronger on one end than on the other end. And that's basically all I'm asking you to look at. Let's look at this, and I'll share some more data. Oh, let me go back to that. Let me give you another nice little beautiful teaser. So VSL did participate per these plans anyway. You know, this is part of that 0.01% where we could be getting sent down the wrong path. But I'm going to accept that path at this point. I'm going to enlarge this, roll it up. Most important part of these the plans for post-tensioning says a seating loss of 0 inches, wobble coefficient of 0, and friction coefficient of 0 have been assumed in elongation calculations. This is the engineer, and it appears that this engineer did this is VSL engineer. And he gave 0. You have no margin of error. It will be 100% what he calls for. I think it's a he. It will be 100% what he calls for. And is this him here? This appears to be that person there. If you look at who it is, it says VSL. That name comes up, and specifically it says specialist in post-tensioning design and analysis. Purchasing change orders and contract negotiations, cost budgeting, financial revenue projects, labor and resource management. Okay, so we got somebody else to add to the fire. As you look at the this is the VSL stamp on there. That's his stamp. This is the post-tensioning, and it speaks of, again, no friction. So I talked about that. I want to know, this is one of the things that I need to eliminate as far as, did they calculate for friction in the and the and when they did the post tensioning, did they calculate for that? Well, he's saying, yeah, it's going to be calculated and it's going to come to 0. You'll have no deductions, plus or minus. It will be 0. That's how I interpret it. All right, now going to the bars, the number 2 and number 11 bars, we have 1.75 inches. It fails at 400 kips. This will be very noteworthy for you guys who all want to know if the bar broke. It fails at 400 kips, and also tells you what loads are on the structure at that time. We have shown that no failure. It says ultimate tensile failure, so so it could be a little bit over, maybe 10%. So you can do that if you want, or we'll just say 400 kips, but it's probably over, maybe 440. So we can say that this structure did not apply 440 kips on any individual bar down there, meaning A or B. Even during failure, when it was ripping out the bottom of 11, it still stayed intact. And so it never had more than 400, and you can probably guesstimate 440 kips. I would think that it would have had some necking somewhere, even if it elongated. If it passed 400 kips, that we'd start seeing necking. There's no report from NTSB about necking, so we can say that it never experienced this 400 ultimate tensile strength failure. That's in A and B. That's what I extrapolate at this point. Now, if they show that in the nodal area of 10 and 9 that it broke free with some necking, then we know that took place at some point, but never did it take place with their post tensioning. They were at 288 kips applying loads. 288, I believe it is, right? Let's find that real quickly. 288, I believe, was the okay, I've got quite a few tabs here. Rods above. 280 kips. And to give you comment to that, if you see it says dead end force after anchor, live end, 280. So it's 280 kips on each end of this period. So you're getting 280 kips on number 2, A and B. All the rods will give you a balance of, these rods will give you a balance of whatever you put on it, that you're done. There's no extra elongation needed to reset back to where you want to go. You want to get to 280, you dial it to 280, call it a day. The elongation is kind of weird on this one. If we look at number 11, A and B, one is 33 foot long, the other one is 33 feet 2 1/4 inches. The kips are the same as number 2 and number 11. The kips come out to 280. They equally loaded it. So they assumed that we were talking, if you guys you remember, we were talking about the overhang, that the overhang is why they did this. Now, if you do your calculations and you see where the transporters are, that means that neither one of these need to be exceeding 280 kips. They didn't calculate, because we know that the distance, the span from each one of those transporters need to be equal then, because they're equally has a resistant force of 280 kips applied to it, a preload, if you will, on the bars. Remember, they don't tap out till they get to 400, but elongation can still happen. Let's go with number 11. Number 11, it says stretch down right here to let me slide that over, 1.39 inches, and only 1.40 inches on the other one, which just happens to be 2 1/4 inches longer. They only moved it 100 thousandths of an inch. 100 thousandths of an inch longer. Remember B and A. So let's bounce out of here. B and A, I believe, this is the way I configure B and A. Just so you know, it could be backwards. If so, just needs a little adjustment in the comments and the video to make it still not be an issue. Just invert it. And you invert what I'm saying. Don't invert it here. So I believe this is A and this is B. B being the longer member, and I base that on that it's out here. But we're only talking 2 3/4 inch length. Let's see, we're talking B, A, number 11. B is 2 1/4 inches longer, these two guys. So talking about the anchorage, A is anchored in the deck itself. It stops short. Let me make sure I can see that. It stops short. It clips it. The back of the plate clips the 12 at the deck. Remember, this is a nodal area This would be like a nodal area the way I'm looking at it, and this is a blister, I call it, in the back, because this is not fully down here like this. This is back here like that, because this is where this anchors the B, post-tension tendon, and number 11 is, and it's in a blister. That blister is then dissected by, below the blister, it's dissected by a 12-inch hole, 8-inch pipe, I believe, with a 6-inch radius when they did it, and then they put an 8-inch pipe inside of it. So that's grout we're looking at, unless they deviated and just made it 8 inches perfect and poured it with the deck. I don't know. All right, so nevertheless, it's still a disclosed 8-inch pipe. It might be 8-inch pipe. I'm sticking with that for now. And for clarity, don't attempt to troll me with stuff like that. Just correct it in the video. If you troll it, I won't share your comment. I won't share something that's not taking it serious. If you're taking it personally, my comments, I won't share it. But if you were to have the same comment to say, look, it's 6 inches per, here's the drawing, I share that instantly. But if you say, you idiot, it's 6 inches, you don't know what you're talking about, yes, I get those messages. I don't share it, your content, but sometimes I will still, if you take notice, I will still put your comment as a comment in the comments, but I'm now posting it instead of you posting it. So I prefer you to post it. Just leave out, the corrections in an attacking way. Just correct it, and you will get your comment left there. I read all comments except for people that are pre-approved. I don't get to see them, like Mark Fisher, professional engineer, 2015, and quite a few other engineers. I just let them post with the limits of, with the limits of not linking too much. Don't link out of the site too much. You take away, you detract from the content. So during the post-tensioning of this system, there was scaffolding, and this is where I'm saying the beginning of the end happened. I have two scaled models here. This one is more my model that I can proof of concept, if you will. Once you post-tension number 11, that loads come down 10. If they went back, well, then you would see no closure here. Now, I don't know how much goes down there, but yeah, there we are. So D1, this is the one that I explained that was just, let me look at the numbers again. D1 was tension before they did 2 and 11. If we look at D1, I'm looking at my laptop. Give me a second here. D1 states, D1 is total of 427 kips initially, but it goes to live end at 471 and 489. So we have 471 kips down here. And 489 down there. This is the failed end. So we're going to focus on that. We also have to establish some playing grounds here. The failure in the video shows here and here. Ultimately, that's where I'm going to. I'm going to the same points. This means it's an post-tension elongation miscalculation. And that can be thrown in quite a few ways. One, I think when they when they added this number 11 by FDOT's request, and maybe that's why you guys don't see FDOT bragging about it too much, because that throws them under the bus for structurally involving themselves in this design, which they did by saying add this on. If this was never there, and they load tested it in the over there, well, first off, it was never there. If this was never there, no post-tensioning could be considered part of the issue over here. But because it was added, this allows that factor to participate. I call you up and tell you to come pick me up, and you die coming to pick me up. Obviously, me calling you to pick you up has a factor in your death if you weren't going to do it beforehand. Well, literally, this has a factor in a death because it was added without 100% following through everything with it. You put your hands on it, you're responsible for the deaths also. We're looking at number 11 to some percentages. So, some percentages of the death. So, as I understand percentages and etc. Anyway, so as you pull on, if this is post-tension, this is only in the deck. This number B, A and B, B is, and I've gotten this inverted in my videos, I apologize for the confusion. So, A and B, this pulls on this, on the back part of this. This is to scale. This is not to scale. This part right here is not to scale. I'm going to zoom in a little bit. So this, what you're looking at here is like an overlap. and this is in a blister. Here's the pipe going through the deck, right about there. As it goes through the deck, everything down here is non-structural. It's done. It's a little 4 inches or 3.5 inches on either side. It's nothing. This means that this column, number 12, being a column, does have 10 inches extending beyond the diaphragm, the deck. It's part of the diaphragm because it was built, it was cast when they cast the deck. It's 10 inches. And then the 12 and number 11 were put on top of there. Before that, though, they ran these bars were formed up to be embedded in concrete. I don't know how they did how they supported it temporarily above, because they still had to pour the concrete. So it must have been obviously outside scaffolding system to hold all these bars off of the concrete while they're pouring the deck. Again, they poured the deck, encapsulating these bars. Now, I don't think they put and I don't see anywhere any type of clamp or anything like in there. I don't see that as part of specs at all, but that's not the issue anyway. I don't think that these elongated to failure. So this 10, as we look at this 12 rather, and you look at the very tip of it right here, this has this weird, this odd, not odd for the design obviously, but it comes over the canopy in this shape here. This is part of 12, and this is the canopy. This is poured secondary, the next cycle. So the uprights are poured, then the canopy was poured, then the blister bars, but as per the OSHA report. This is an odd duct, but nevertheless, it held together. But I'm showing you that the forces are inside this member. That when you post tension, when they post tension the canopy, it has a clamping force, and any deviation from this canopy downward would create a kicking out of this direction. Also an elevation of this, which I showed in the previous videos, that once the deck started deflecting, the canopy deflected. All this did was it shear when they released this. Oh, I'll get to it. I'm sorry. Let's back that up. Let's back that up. Let's go back to the post-tensioning again. So now we have the post-tensioning in number A and B. I don't know if it's Erica or who called out for it, but they called out that D1 only. Remember, D1 only is the center of the deck. Let's go to the next part of the video, and we'll keep on moving. I'll come back to that. I believe this is all being done on the fly, so you can imagine how I do presentations. So there's no notes I'm reading from. Not yet. I do have some memos that I want to make sure I go over. For example, D1, 471 live end. Okay, so D1's, and this is not to scale. My white balance is off now. I got red skin. All right, so D1, and this would be D2, etc. Now I foamed this up to help you see how loads work. This is actually would be this foam on the bottom I'm using as reinforcement, taking some liberty. So yeah, but it's going to help you see like a free body diagram. Again, it helps you visualize it. I can visualize it and see that the mat, if you will, of the reinforcement would create a resistance, and that resistance is going to come back into play now when VSL called for zero wobble, zero coefficient of friction, and clearly a mat would offer some resistance when they go to post-tension this. And D1, I don't know how you can call for that. Obviously he's party to somehow the D1 going first, and then they post-tensioned number 11 and number 2. Upon post-tensioning number 11 and number 2, let's go back to here, and this is a good enough angle for that. Let me zoom in just a hair. Okay, put down my notes. When they post-tension number 11 and number 2, I think they drove forces down 10. The scaffolding, let me come over here. The scaffolding is very important to me. The scaffolding, I think, is not on a foundation, and this bridge creating a different flow path once you post-tension it down the members. that it pushed down on the scaffolding, buckling it, deflecting it, and or also the impression in the dirt. Upon 6 days later, upon the engineer now speaking on the cracks he sees in number 10, he calls them a tension crack. I think he did it, and he did it. I think that's a mistake. As you can see, this is like a tension crack. It's open. It's open. In reality, I cut it away. But watch what happens when I push it closed and then release. Of course, this is you have C2 and D1 in there, so I'm taking some liberty, I think, to some degree. But you can see how it opens back up. Remember, there are bars in here, 4 post-tension bars, but they have not been tensioned yet. These have not been grouted. They've been applied but not grouted. So this would allow for a break inside this ductwork at this time, once they post-tension this to 288 kips per end. It's 288 kips. It's on each end of this bar. So as I pull on this, I'm going to use my foot here to act like scaffolding, just to show that if I post-tension either one of these, and I've got to take some liberty there, that it closes just so slightly. Now my tape's sliding on me. Same thing with this one. That I'm showing basically the forces go back down 10. Now if I were to move my foot, you clearly see it move. And what's it doing? It's anchoring there, pulling here, and there you have 288, you got 596, 600,000 pounds of force in this unit up here. Some of it's going down 10. I think it caused deflection in the scaffolding at the point. And 6 days later, when he looked at it, I think it rebounded. They were further down the line with their post-tensioning and what they were doing. He was trying to evaluate it. Even asked the CEI, even asked the engineer of record to establish what's going on, per the memos we see. That ultimately he's asking the engineer of record, hey, are these expected? At least what we think is cross-sectional tension cracks from the steel. Now, he said cross-sectional, interesting. The cracks are, as reported, as I look at the measurements, they appear to go this direction, 1, 2, and then 1, 2. He says measure from the bottom. I don't know if there's a bottom inside here, or the top of the deck. I don't know what his bottom is. So you have to move these, but they're parallel. The reinforcement goes in this direction in these members, as we saw in the OSHA report. The stirrups go in this direction. So the cracks, as described in the memos, appear to go this direction, which is parallel with the deck and canopy, which would give me that break, that release of tension. Now, so he did the release of compression. So then I have a deflection here that's rebounded. We only have C2 in here. C2, as you remember, C2 is, hold on, .426 and 459 kips. So down on this end, we only have 426 resistant pounds of force, if you will.